Hi, everybody. Yeah, I'm gonna do a couple, one or maybe two videos, going through the ideas of an electric field, electric potential energy. We'll talk and then also about voltage, and then we'll talk about why we need to use voltage as opposed to the idea of electric potential energy instead in a circuit. Okay. So I am going to go a little fast, so feel free to pause, rewind, make it slower, whatever it is you want to do. All right, yeah, I had you guys do this charges and fields simulation, and also a simulation on electric potential. So hopefully you've figured out by now, right? Electric fields, similar to gravitational fields, but where gravitational fields only have the field lines. So I got a gravitational field right here. Like if this is the Earth, right? If this is the Earth right here, then the gravitational field always points towards the center of the Earth. That's how the gravitational field works. More on that in just a bit. So electric fields have a similar convention, except it's when it's negative charges. When it's negative charges, the electric fields go into the charge, and then the electric field lines point radially out of the charge if it's a positive charge. So positive charge points out, negative charges point in. So that's just a convention that was established long ago. So the definition of an electric field is very similar to a gravitational field. A gravitational field is the amount of gravitational force per mass. So if you have some mass, that mass interacts with the gravitational field, and that produces a gravitational force. That's kind of the idea behind the field, is that, so if you had something like the Earth, right? The Earth, we say, exerts a gravitational field, and it's not until you put something like Sandra Bullock in there, and that way then it produces a gravitational force as a result. So the field is the mechanism by which physicists use to talk about how force can act over a distance. Same idea with the electric field. Exact same idea. Is that an electric field, if a gravitational field is the amount of gravitational force per mass, the electric field is the amount of electric force per charge. And so we can kind of rearrange this just like I did over here. And basically, again, it's how the mass, that's the property that you need to create a gravitational force, interacts with the gravitational field that produces the gravitational force. So the same way here, it's how the charge interacts with the electric field that produces an electric force. So charge being the thing you need in order to create an electric force, right? So once again, if you just ignore this charge right here. So if you have a positive charge like this, it's going to create a field, but it's not until another charge shows up to interact with that field that you then get, if this is a negative charge, let's say, or if it's let's make it a positive charge. If that's a positive charge right here, it's going to produce a force that goes like this, and it interacts with the field, and there you go. So hopefully you can see those definitions are the same. All right. Another way that I thought was really easy for me to visualize electric fields, why electric field positive charges go out and negative charges go in, you can kind of imagine like water. In fact, electric fields were imagined using the ideas of water and how it flows. So often positive charges are called electric field like sources, and negative charges are electric field sinks. So you can think of water. If you were looking down at a drain, right, the water would come in, down at a sink, the water would come in from the faucet, hit the sink, and then spread out, right? Where if you got the sink part of the sink, the funnel, right, that all the water would flow down inward toward it. So that's what gives us, if you looked, down directly, you would see from the source, from the faucet, the water spreading out, and then from the sink part, you got the water going in, and that's the idea, like a positive and a negative charge. I don't know. That just helped me kind of better visualize that. Anyway, moving on. So we're going to get to this idea of energy, and this is nice practice for you in stuff we've done with conservative forces, right? We know the idea that a force, right, is the derivative of potential energy over position, the negative derivative, right? And that'd be for a conservative force. This works for gravity. It works for springs. Any kind of conservative force will do this. And it turns out the electric force is a conservative force. So it also obeys this idea that the work done by that conservative force is equal to the negative change in potential energy. That's a big thing we did in AP Physics C. And so we're going to use, I'm going to change this to K. So that's just a constant. So we're going to use this idea to see how, if we can get a potential energy function from this. If you want to try this yourself, go ahead and pause it and see if you can integrate your way to try and figure out what the electric potential energy function is. So here we've got two positive charges. And one of the positive charges, we're going to move from A to B. And as we do that, the electric potential energy should decrease. So, all right, let's go ahead and try that. So, and so we'll use this equation. So the change in electric potential energy is going to be the negative force from A to B, and then the force, that's going to be the electric force dotted with dr. So again, that's basically rewriting this. It's going to be negative A to B of the electric force dr, and then cosine of the angle between those two vectors. So my dr is moving this way, right, where the force is also moving in the same direction. Right, because it's this charge 2 is going to be repelled by charge 1. So that makes the cosine of 0, so that's going to make this 1. So that's that, all right. And then now I'm going to plug in the electric force equation and see what's going to change as we move here. So it's the integral from A to B. The electric force is a constant times charge 1 times charge 2 divided by r squared, and we're integrating with respect to r. So the charges and this constant are not going to change as we move from one position to the next. So I can actually pull those out of this integral here. So I'll say then the change in electric potential energy is equal to the negative KE Q1 Q2, and then we got the integral from A to B of 1 over r. That's the same thing as saying r to the negative 2. It's going to make my integral easier. And so you can then integrate, because now we're just integrating with respect to r. I'm going to add 1 and then divide by what I have left, which is sorry, it's going to be negative r. So, sorry, negative 1. God, I almost forgot how to do an integral. So yes, I added, so instead of dropping down and then subtracting 1, we add 1 and then divide by what we have. So we got negative 2 plus 1. So that's going to be negative 1. And then that negative 1 gets dropped into the bottom here. We divide by negative 1 to do that. So now I've got the change in electric potential energy. This negative is going to cancel with this negative, and that's going to give me, so this is going to go away. So it's going to give me KE Q1, Q2, and then r to the negative 1, that's the same thing as 1 over r. And then we're doing this from A to B. So, and that's going to give me my Coulomb constant, Q1, Q2, divided by r, going from A to B. And basically you can see the general form right here, but if we did that from A to B, so we could say going from position B minus A. So it'd be from position B to A. And so where this is R, but basically the general formula that you get is that the change in potential energy, or the potential energy equation. I'm not going to go too much into because it behaves similar to gravity, how we say when you go to infinity that it goes to 0. I'm not going to get too much into that. I'm just going to say right now that the potential energy equation we have is essentially this. So this establishes our potential energy, and as you can see, it's very similar to the gravitational potential energy. The only difference is with gravitational potential energy, it's negative only, big G, M1, M2 over R, which we derived in class back in AP Physics C. Okay, so moving right along. Gonna let you look at this for a moment. Pause it if you want to. And hopefully this looks familiar. This might be something that you've seen. I think we've, when we talked about gravitational fields, we used this kind of analogy. And this is a topographical map. So it's a contour, these are contour lines, and basically it's a map, but these lines, these circles here are indicating elevation heights. Or elevation. And so, right, like this could be, let's say meters. This is 20 meters, this is 60 meters, this is 160, this is probably the top of some mountain that's 400 meters up above. And you can see if I walked up this path this way, this is much steeper because I'm, as I move in my position, I'm increasing in height really easily, where over here it's much easier, right? It's, there's not as big of a change in elevation as I move through a distance. So, yeah, and so, right, so yeah, it's a topographical map, and you know, we could do things like place a mass, a ball here, right, and let it go. We know that it would fall down, you know, like that, like this. So yeah, and basically this is working exactly like, so you guys made, again, a PhET simulation where you did, you found out, you made electric potential maps. So it's this idea of electric potential, not electric potential energy. Electric potential energy requires two charges. You need two charges to create electric potential energy. The electric potential is a lot like the idea of an electric field, just a scalar or energy version of it. So it's like yeah, electric potential is like a scalar version of a field. I'm going to use the idea of a gravitational potential in a bit, but right, an electric field does not need a charge to exist. So it does not need a second charge to exist. An electric field just needs one charge, but a force needs two charges to exist, right? It's that charge interacting with the field that produces the force. So it's the same idea with potential. So if you have a charge or charges, like you guys, again, going back to the charges and fields lab that you did in a bit to review that. So you can kind of think of like height or elevation as like a positive charge. So if you're up on a mountain, that's like a positive charge. And then a hole is essentially like a negative charge. So it would be a negative charge. And so yeah, that's why we tend to call negative charges low potential, and positive charges we call high potential. And so, all right. I'm going to probably mention this again, but I'll say it right now. So the idea is that, so similar to gravitational potential energy, I'll bring this up again. Actually, I'm gonna go to keep the visual right now. We'll talk about those later. So let's see, going to this website. Hopefully it loads up for me. Here we go. So what I like about this is it shows you kind of what I mean here. So when you guys were looking at your charges and fields lab for your potential part, oh, come on, load up. So we can go to this equipotential view, and so you've had like a positive charge right here and a negative charge right here, and this is like your sensor that you guys had that showed you where the electric field points, right? But you can see the potentials here, I think, are all equal changes. So like, yeah, it looks like here's about 20 volts, here is 30 volts, here is, it's looking like 35 volts, That's about 45 volts, so maybe it's more like 15 or something like that. Well, anyway, and you can see it's steeper here, right? It's a bigger change, and then it's more shallow here. But basically, this is like a hill. This is a positive charge, and this is like a hole. This is a negative charge. So when I look at a 3D view of this, I get, oh, yeah, that makes much more sense now, right? So here's where the positive charge is. You get high potential happening here, and here's where a negative charge is, and you get low potential. And so things with positive charge, if I were to let go of a positive charge here, it falls from high to low potential, just like if I dropped a mass here in a gravitational field, it would go from high to low potential. However, kind of strangely enough, if I put a negative charge over here, it actually falls up. So if you just let the negative charge go, it would feel a force from this negative charge and be attracted to this charge, and it would go into from low to high potential, which is kind of weird. So you can, something to think about would be, oh, if I had negative mass, right? Oh, I would fall up into the sky then. So good thing we don't have negative mass, because that'd be terrifying. All right. Anyway, so that's a nice little visual right there. And so, yeah, and you guys did things like this. So again, here's the positive charge. Here's a negative charge. I have more or less equal potentials here. And again, we call this high potential, and this down here is low potential, near a negative charge. Yeah. Okay, and then these lines here, so when we're talking about elevation maps, they're called contour lines. These are called equipotential lines, literally meaning equal potential. So the potential is the same at every one of those points. If I were to think of it like like if you were on stairs, right? If I were to walk around like a set of stairs like this, I would just stay on that same set of stairs. I wouldn't change in elevation. So the same thing here. If you're on this line, your voltage is negative 10.4 volts, and it stays like that. So again, positive charge is like a hill, negative charge is like a hole. Plates are used a lot. If you go on to physics E&M, you'll see a lot of these plates. And essentially they do that because the electric field stays fairly constant, and the difference in potential stays fairly uniform as well. So these are kind of called parallel plates. So you got a positively charged plate and a negatively charged plate. And then you can see the distance. So each of these are equal differences in voltage. They're about 10 volt differences. And you can see the distance between them, literally the distance between them is pretty uniform here as well. All right, and then something else to note is that electric field lines always point perpendicular to the equipotential line. So you can see the electric field line is, so here's the equipotential line, the electric field line points perpendicular to that. Here's another equipotential line, the electric field points perpendicular to that. Here's another one right here, so the equipotential line is like this, the electric field points perpendicular to that. So it's a, kind of conventions there, okay. Moving right along. And again, you guys were asked, so if you just had a single charge, not like a plate or anything like that, and you were to drop off at equal distances, you can see that the voltage is not constantly dropping off. So there's kind of a weird relationship going on here. We talked about that already. So, all right. Well, okay. So now I'll go back into this idea of what potential is. There we go. Sorry, switching around all over the place. And I'm going to do it similar to gravity. So this idea, and then I'll talk about why this is necessary in just a bit. So gravity, the idea of, we haven't talked about this, so but I'm going to do it to define electric potential, which is the idea of gravitational potential. So the idea of gravitational potential, similar to the idea of a field, right? A gravitational field, we said, right? Oh, there it is over there, right? We said the gravitational field is the amount of gravitational force per mass. Well, similarly, gravitational potential, we use the symbol V for potential, is the amount of gravitational potential energy per mass. So you can see it's the same kind of idea. And so that same idea here is that you've got electric potential, and that's the amount of electric potential energy per charge. So yeah, and we can use our equation for a point charge of electric potential energy that we did before. So we said a point charge of electric potential energy is Q1, let's say a source charge times Q, the object. This is the thing that is interacting with the source charge, and then divided by our R, which is what we had, and then over, let's say, our object charge again, and that's going to be our electric potential. You can see the charges, the object charge cancels out, and we get left over that one equation you can do to calculate the electric potential is Coulomb's constant times the source charge divided by R. So that's an equation you might see. We're not going to mess with it too much, but you might see that if you go on to take your E&M class. Okay, so yes, potential is measured in volts, and let's get more of like a conceptual idea of what potential is. So again, hopefully you can see the similarities, right? Electric field is the amount of electric force per charge. So electric potential is the amount of electric potential energy per charge. Just like the same idea that a gravitational field is the amount of gravitational force per charge or per mass. And then gravitational potential is the amount of gravitational potential energy per mass. Moving right along. So you can probably imagine I got situation A and situation B right here. And in situation A, you got a 2 kilogram mass that's at a height of 5 meters above. Here you are at the bottom, and you want to know how much potential energy that is. And you can say, oh, that's really easy. Or sorry. And then here's situation B. It's a 50 kilogram mass, same height, 5 meters up. And you want to know, we'll say we're really near the surface of the Earth, and you want to know what the gravitational potential energy is here. And which one is bigger, A or B? Hopefully you can just look at this and go, oh yeah, I know which one's bigger, but we can calculate it out just in case. So yeah, so gravitational potential energy, it's the mass, 2 kilograms times 10 times 5. So it's going to be 100 joules of energy there. Okay, what about here? So using the same equation, it's going to be the mass, which is 50 kilograms, times 10 times 5. So it's 50 times 50. That's, I hope I get this right, 2,500 joules. And obviously, right, this one, situation B, has the greater potential energy. Easy peasy, no problem there. So now I get you with a new situation. Instead of having a rock at the top, you now have a flowing river of water. It's at the same cliff. It's 5 meters up, right? So yes, calculate the gravitational potential energy. Wait. Yeah, you can't do it, right? Because you don't know what the mass is. So how much mass should I give you? Should I give you this much mass? Should I give you this much mass? How do you say what the mass is for flowing water? Yeah, that's really tough to do. And this is the whole idea, the whole reason why we can't just say electric or we can't just use potential energy anymore, because when we start to get to, this is the idea, right? We don't know what the mass is, but we could define possibly to get an idea of maybe, right, how much potential energy each mass has, right? So how much potential energy per kilogram maybe. And to do that, we would define this idea of potential. That is the amount of gravitational potential energy per mass. So, and this is gravitational potential. So gravitational potential then would be mgh over m. Oh, and then the mass cancels out, and you get then gravitational potential energy is just the gravitational field times the height. So it's kind of like, and this is kind of weird to think about, the potential to have potential energy. It's how much, right, potential energy, potential, like basically that 1 kilogram of mass would have at that height, right? And so you can see, right, the gravitational field could change, but in this case, if we're near the surface of the Earth, the gravitational field ain't going nowhere, so we could change the height. Here is less potential than here. So the potential at A is less than the potential at B, et cetera, et cetera, et cetera. So, and that's kind of the idea. So again, the idea is freely flowing water, we can't really calculate a definite potential energy unless you give us how much mass you want to talk about. And this is the idea within a circuit. A circuit is going to have freely flowing charge, right? And so we can't really say what the potential energy is for freely flowing charge, because it could be, it could be like like the Amazon River, and there's just a bunch of water flowing through, or it could be like a small little creek, right, and not much water flowing through, or charge flowing through. So this idea of potential energy kind of loses out, and this idea of potential or voltage gets a little better. So to give you one more kind of idea before we leave, before we get into circuits here, you can kind of consider this like a battery, where a battery has a certain amount of voltage. So in a certain field, it's at a certain height. Well, more on batteries a little bit later. So, all right, and so so there's a set potential, and then here it's 5 times the gravitational field, which is 10. So that's going to be 50 volts, right? 5 times 10, height is 5, gravitational field is 10 newtons per kilogram. So you get 50 volts that you're working with here. And again, you can use a lot of energy by assume that you're here, you can control the flow of water. So here's you can control the flow of water. And so you can do a lot of water flowing, right, and that would make a lot of energy, or you can do a little bit of water flowing, that make a little bit of energy. And this thing you thought was a sun was actually a water wheel. So right, because then I could I'll go back to energy right now. So let's say with this amount of water, I have 100 joules of energy right here. And without the water wheel, right, all that energy, all that water would turn into kinetic energy when it reaches here, and it would have 100 joules of kinetic energy, right, at the end here. So this would be the gravitational potential energy, this would be the kinetic energy here. But I could move my water wheel over here and take some of that energy. So if I do that, right, and let's say, right, well, if I do that, the wheel's going to spin. The wheel's going to spin at some angular speed, and now I'm going to have less energy for this water at the bottom. Maybe now it's going to have, let's say 40 joules of kinetic energy at the end. Well, if that's true, then there must have been some energy needs to be conserved. So that means in order to spin this water wheel, it must have used, so this is rotational kinetic energy, and that must have used 60 joules of energy. And then I could use that energy to spin my water wheel, and use that spinning water wheel to, I don't know, move a box or something back and forth, right? You could put a little lever here or whatever, and then I could move a box back and forth, and that's useful work. Or I could attach it to, my TV, right? And then I could use that, energy, right? Let's say it's perfectly ideal and I get exactly 60 joules out. Not going to happen, but whatever, right? And I get that 60 joules for my TV there. But then let's also say I want to, run a small little clock, right? Well, this TV is going to need much more energy than this clock, right, is going to need. So I would need, maybe 60 joules here, but I would need maybe 2 joules over here. So how can I divvy up that appropriately? And that's where the idea of potential is. You get to control, right, how much water flows through. So let's say you allow a lot of water to flow through here in order to make the TV work. But then I cut out another little waterfall here and only let a little bit fall, right? Well, that then I could run to the clock and help the clock work. So that the clock gets those 2 joules, and the TV gets 60. So that's kind of the big idea of a circuit, using the analogy of a gravitational field. Gravitational potential. So the same idea applies with electricity. So the voltage, and we just use V because, again, gravitational voltage, not used much in physics. Or gravitational potential, both mean the same thing. Electric potential or electric voltage, that is used a lot. And so, again, electric potential is the amount of electric potential energy per charge. So here you go. The electric potential is the amount of electric potential energy per charge. All right. So starting circuits next. Bye.